This kind of like detailed intro story lined up here, but I really do like to keep my videos more off the cuff. I do want to have a bit of a like outline so I know what to go off of, not a script at all, but like something that I can ground my thoughts to a little bit more. So I'm going to do that. But as far as the intro for this video, the bottom line is to me, I look at this overall as the Amazon internet moment, right? We're at the like internet 1999 currently right now, and the big like 98. And the big question is essentially like, how do we monetize AI? That's what everyone wants to do. That's like the number one question in like with all the people that have money, right? Whether or not that's your question or not, that's like the question, right? That's the question that is going to matter and basically shape like anything moving forward. The answer to like how that goes down. And then how that went down the first time is very simplistically with the Amazon model, right? And the Amazon model is to pick a part of it and then like monopolize that certain part. And then within that and within AI, the all of the money is focused on the data. Like you've been seeing like I've been seeing like for the last few years, you've been kind of seeing like the money like float around, like where is the point? Trying to find that point, that mechanism, right? And then you can see now that everyone has honed in on that equation. And when I mean everyone, I mean like private equity, hedge funds, like big corporations, etc. Like you're like all of this talk about data centers, and then so within that, that's the kind of piece that has been decided that this is what we're going to do to move forward with like what would they want to be like web 2.0, so like AI 2.0, right? Like more monopolization control within that. Like the problem that I see within that flat out is that particular take has a complete misunderstanding of physics overall and how these models actually learn. Like I think we're actually setting ourselves up within this for like a massive loss of massive amounts of money within the economy coming up as people realize that this is the wrong bet because it's so much money. Like if it was like a casino, right? Like all of the money is on data. Like 100% of the money is on data. Then like there's like 0% on the other side, right? I'm like, here's I'm your one bet on the other side. And then my one bet on the very side is very simplistic, which is that the models don't actually learn from the data set itself. They always learn from an abstraction of the data set, one layer below, one layer removed, the undercommons of the data set itself. And then so within that, I don't think that the like betting on the data set is a good bet. I think everyone that does that is essentially going to lose their shirt. And let me break this down to you in as a simplistic way as I can. The first thing that I want you to understand is that models actually operate in real space. Real space has physics attached to it. And we can see this, and I can prove this up and down via experiments, like changing the model and the way that the model works and operates in like Euclidean versus hyperbolic space or fractal space, different dimensions, right? If you look at IJEPA models put out by Jan LeCun, they have a hyperbolic layer very specifically built into the model, right? There's a layer, one layer of the model that operates in hyperbolic space. A very interesting and unique concept, right? Like the hidden dimension. and then so within that and within that space, he purposefully builds it in because he understands that there's physics attached to these digital spaces. And then so whether or not it's a digital space or not, it doesn't matter. It still has physics that applies to it. And then that also applies to concepts like entropy, right? So then entropy in hyperbolic spaces has a higher speed limit than it does in Euclidean spaces, for example, or fractal spaces. And then that's just like, parts of physics. And then also within that too, real space has dimensions, and then real space also has limits. And then this also applies to digital space as well. right? So then if we set, for example, up a digital space, and our digital space includes the knowledge that a model knows, like that model is set up and that knowledge is distributed via dimensions. In that instance, that would be the layers of the neural network. And then so if it's 15 layers, and then it's that data is distributed, and that space, that data space is distributed across 15 dimensions, and then it also has structural limits, right? So the model is measuring distances between concepts is essentially how it's doing it, and then there's structural, mathematical, and physical limits as to how much distance can be in between those two spaces, like between, like, say, dog and cat, right? Those would, like, just using those as easy terms to say that those could possibly represent like two ends of this universe, of this space, right? This digital space that would exist, and those concepts of dog and cat would be at opposite ends of the digital universe, but those opposite ends would represent a real limit, right? And then that real limit is like if you make it too far, like because the model will do like cosine similarity, like all kinds of distance calculations, right? Like Fourier transforms, etc. But it's measuring and utilizing kind of like a probabilistic blend of measurement, which is why I can't say it's doing like, like this, and this, because it's every model does it like probabilistically, and they blend these calculations, but they're distance-based calculations, but there's only so much compute that the model can handle within that distance. Overall is the big concept to understand within that. So step one, models operate in real space. Step two that we need to understand within this is that intelligence is entropy compression. Intelligence as I'm defining it in this instance, right? And there could be a whole different layers for intelligence, however you want to define intelligence. My definition of intelligence in this instance is taking a problem set and then iterating and solving on that problem set. I'm trying to keep the definition of intelligence as simple as I can in that instance, and then very broad too, right? So within that, my definition of intelligence, how essentially I think that like intelligence comes about, is the very first step is that you have resonance, like say, resonance being like harmonics, like a tuning fork, right? And then so you hit the tuning fork at the right frequency, that then generates geometry. Hitting the tuning fork at the right frequency can turn that into like an actual physical shape, right? And then so that gets you geometry, and then you break down resonance plus geometry, that gets you to electricity. And then so when you combine resonance, geometry, and electricity, what happens, and you introduce that into an environment, and you have agents in the environment, they start clustering together. They start wanting to get form like compression in the environment, which leads to compression in the environment, which then leads towards like my definition of intelligence in that instance, right? Because it's just compression. So then like utilizing the example of slime mold being able to solve like maze puzzles or optimization puzzles, etc. How does that do that? Because slime mold would be step one of intelligence in this instance, right? It has that compression mechanism that comes about because of step one, resonance, step two, geometry, step three, electricity, step four, clustering, and then step five, it has compression, which leads it to step six, which would be step one of intelligence, right? And then so within that, entropy compression is the measure of disorder within a system. And then so if you look at kind of like all of the recent research and like all the cutting edge research within AI, it's all around entropy compression and this concept, right? Like there's nothing at all like controversial around that whatsoever. But then so what that means within models very specifically, and a component of that I think is controversial, that a lot of people are just failing to overlook and are paid to overlook, is that so transformers, the way that they work and they interact with compression is that they prepay compute. And then so that's what we've discovered since 2017, right? Like, why does this model work so well? What is it about this architecture that works so good? And then so essentially what it is, and the reason why like you take like massive amounts of data, gobs of data, right? And then you just feed it into the model, and then by doing this, you're essentially just like taking your all of that data. You're like loading up like a credit card limit, okay? And then like the more data that you're loading into the model, the bigger and bigger that credit card limit gets, and then you're just prepaying. So then you're like you can use your credit card to like perform functions, right? Mathematical functions, computational functions, whatever. And then the transformer architecture as it's built just happens to be the way that the physics operates. It works like a credit card compute system, whereas like other architectures don't work like that, right? And then so by loading up all of that data onto your credit card, you just are prepaying your credit card limit. And then like if your limit is big enough, you'll solve the problem, right? And then you'll have like, you can overdraw your account. Maybe the bank thinks that you're in a different location, things like that. So things will happen where you'll have like hallucinations that will occur within that, right? But generally speaking, that's what the transformer process breaks into and breaks down to on that level. So all of that's like very good for transformers architecture as a whole. The problem within that is going back up, right? One layer back up, where all of this is based off of entropy and entropy compression. So in order to be that credit card, right, like that mechanism and how it works and how it's doing that, how it's prepaying, it's leaking entropy in the process to do that. Like think of it like converting energy to like anything from like energy to like gasoline to fuel a car, right? There's always like an energy leak. It's never a one-to-one conversion. And it's the same thing with how transformers models are operating, right? They're not converting the data 100%, like would they, and it's very low conversion rate, which is why it takes so much data, right? They're like, because they're leaking entropy throughout this whole entire process. So like as they're going, like they're taking like your massive gobs of data that you're prepaying for, but you're not getting like a one-to-one investment return on investment on your prepayment. You're prepaying like let's say like a big cost, right? Maybe it's like you're prepaying like an extra 70%, extra 80% in order to like get that benefit of having the credit card computer that you can just use later, right? So the big concept within that is that it's cool. And then so if you're like scaling it up to like 1 trillion parameters, then you're basically like scaling it up to like an Amex black card, right? Is like what you're trying to do. And then if the limit's high enough, if the credit limit is high enough, you can do that. But the other thing to keep in mind within this, and so if you understand that concept when it comes to physics, is that P equals MP or P doesn't equal MP, right? And then so as far as we know, P doesn't equal MP in every equation that we've been able to process it out. MP equations are harder for classical computer models to compute than they are for P problems. And then prepaying and putting it on the credit card doesn't overcome that, right? And then so these models do fall into the equation where NP problems are harder, right? And then so if your credit, like even if you're just like balling out with like an Amex black card, if you're trying to put mansions on it, like you're gonna like bankrupt the card really quick, right? And then so that's the same type of concept here. Like just because you get the Amex black, like that isn't the end all be all. It has to be paid down, and you can't just go like flipping yachts and mansions onto an Amex black card like every 5 minutes. And then so the kind of the tying this all together, the concept to understand is that learning occurs from environmental interactions overall. And then this is like the most important concept to understand within this whole entire equation, and why data centers are basically a house of cards waiting to crumble within this equation, right? So data itself is an environmental interaction. Like think of it like so the an LLM model, when it's training on a data set, like a transformers model as we're talking about, when it's like it's going through its training environment, let's say supervised and unsupervised learning. Let's leave like reinforcement learning is it's a different environment than a data environment. Right? So then it's training on two different environments. But so then we'll leave that out. But we'll say just the data, right? Traditional supervised and unsupervised learning. It's learning, and then its environment becomes the data, right? And then that's what it knows. That's what it interacts with, and then so it's forming environmental interactions and that whole process within that. But the important thing to understand, and I'm going to make it crystal clear 100% within this, is that the environmental interaction and what it does, like it's not distinctly based off of your data. And that's the concept that I want to get into, because of concept number 2 within this, that the data is a platonic form, right? And data is a platonic form of a problem set. And there's 2 concepts within that that are extremely important to understand overall. So first of all, the environment that concept number 1 is that data is an environmental interaction, with data being the environment. Now, concept number 2 is that data is a platonic form, which 1 means that it's not real, and then 2 means that it's itself an abstract problem, right? And then in this instance, it's or an abstraction of a problem in this instance. And then in this instance, it's the abstraction of a problem set, whereas a lot of people think it's the abstraction of a solution set. Like, even if people understand that data is a platonic form, I think a lot of people think that data is a platonic form of a solution set as opposed to a problem set. And then so I put that distinction in there. And what I mean by that very specifically is, let's say that my data is, I want to increase conversion, like marketing conversions, right? That's the data that I'm giving my model, and I have like 5 years of data. So I give it I have 300 dimensions. If I'm going to give it everything, I'm going to give it like everything that it would want in order to compute and then be able to tell me what the future is based off of this data, right? So, but that data itself doesn't contain the solution, because the solution, what I'm looking for is like, what is the how is it going to increase tomorrow, right? How is it going to increase via inherently something that is not in that data set? I'm asking for it to abstract from the data set. So then therefore the solution doesn't lie within the data set. And then when you're breaking this down and understanding that from this particular perspective, that's very important, right? You're not actually giving the solution to the model, and it doesn't exist in the platonic form of the data set that you're giving it. And a lot of people think that they are, right? That the solution is inherently in there. But no, it's the platonic form of the actual, your best platonic form of the actual problem set, right? And then there could be different platonic forms of different individualized problems, which is so meaning that my marketing data could be better than your marketing data, and then so my platonic form would be closer to the actual platonic form in that instance, right? But all of this is again, when we're talking about platonic forms, we're talking about constructs overall. And then I think that gets heady for a lot of people to understand, but I want to break it down and make sure that it's understood on that level. And then so kind of the bottom line within this, right, the ultimate level within this, is that the models ultimately learn an abstraction of an abstraction, and then this becomes their environment. So the environment is the model is learning on data, which is a platonic form of a problem set, and then they're learning on an abstraction of that data. So an abstraction of an abstraction, right? And then what do I mean very specifically, and concretely, by this abstraction? Because this is the most important part of this to understand, right? And then so let me break this down to you as visually as I can. So this Google Colab notebook explores the concept of a resonance in the undercommons, a metaphor for understanding complex data relationships through a simplified, lower dimensional representation. The notebook simulates a dynamic resonance field that captures the underlying structure of a high dimensional data set. And then so I'll give you the process here, what it does. The bottom line, and to showcase within this, I'm showcasing two things overall within this, right? The first of all is that this is utilizing all resonance-based computation. So no like traditional linear algebra, linear math, etc. Like no traditional matrices within this. It's all just pure resonance-based. Resonance and harmonics based computation, and then so the benefit is that this computes in 6 seconds overall, as opposed to like anything like that would be like matrix based essentially. And then so what we're doing, and I'm doing the same thing that we would do with the matrix based model, which is I'm taking and I'm creating a synthetic data set, in this instance a 10-dimensional data set, and then I want to categorize it. But in order to do that, what the model does is it takes that 10-dimensional data set and it creates a 2-dimensional representation of the data set, and then that's where it's clustering, right? And then that's where we get here, and then we can see the model is doing it, yay, with 100% accuracy within this instance, right? Super cool. So it's able to fully cluster these out. But remember that what I'm doing is I'm taking a 10-dimensional data set, and then I'm making it into a 2-dimensional data set, right? So I'm creating a 2D grid and a 2D field, and I'm projecting this 10-dimensional data set, this 10-dimensional space, I'm projecting it into 2D space, and then I'm creating a 2D grid based off of that 10D projection, and then I'm like Plato's allegory of the cave, right? This is like what it's a projection on the wall, right? Like there's the fire is I'm creating the fire, like the 10-dimensional dimensions, and then the fire is creating a shed. The fire is projected onto the wall onto 2-dimensional space, and then on the 2-dimensional space there's a 2D grid that's created, and then that 2D grid is actually what the model is computing off of, right? So the model is computing off of that 2D grid, off of that projection. And so it's never actually it's not the actual data set itself in any instance whatsoever, right? And then this is how the models always learn. Like they're always reshaping and projecting this data into different ways, into lower dimensions, higher dimensions. If it's 2D data, sometimes they'll need to scale it up into 10D data. Like if it's the 10D data, or 100D, or hyperdimensions, where it's like a hyperdimensional computing where you're dealing with like thousands or 10,000 dimensions, those sometimes go from like 10,000 dimensions to 2, and then or anything in between. Like you could program it to go like 8 dimensions or 10, or have it dial the dimensions in between, right? And then those would become the different models, and then the different ways of learning essentially in this instance, right? And then so I guess the question would be and would become so then what's the best framework overall within that, or the ultimate model to build within that? And then to me, I think that's a misunderstanding of this framework overall and how it works within that. What would be the best human in that instance, right? There's too many variables, and it's to me the diversity is what of the population is what actually increases the benefits of the population overall, right? And whether it's a AI structure, human structure, it doesn't matter, right? That's just a simple physics of the environments overall and how they work. And then so models are like that, algorithms are like that. It's all just physics based overall, to me, at the end of the day, when it comes down to that equation and how these things are functioning within these concepts. But bottom line, bringing it all back up to the top, is that again, this all goes to show that data centers are a house of cards waiting to crumble. There's so many people that don't understand this abstraction layer, and then so just shoring it up 1,000,000%, making it crystal clear. So what, right? This is an abstraction, and then so a model takes it from 10D to 2D, or 2D to 10D, whatever, right? But then so what I can do then is I can recreate those interactions, and if I have enough information to recreate the interactions synthetically, then I can do that. And then these models are powerful enough where if they can interact, if they can essentially recreate your data set overall and recreate and extrapolate from your data set to future accuracies, then they can do the same thing, right? I can take a minimum amount of data and then project it up to your data set, basically. Like, let's say that what you want to do is like your problem set is a house is to find like the best marketing algorithm and increase your conversions by 30%, right? And then so that's like essentially if you do that, that's the full car, the Rolls Royce. But then you give the model the bolts, right? And then you have it train on the nuts and bolts of the Rolls Royce. And it's able to reconstruct the Rolls Royce based off of the nuts and the bolts, right? Okay, cool. But then so then you just give me the nuts and the bolts, and then I can reconstruct your model. Right, I can reconstruct your Rolls Royce off of the nuts and the bolts too, and then so I don't need the full data set, right? So then it there's no moat within that. It's like the biggest thing I can't stress enough, right? There's no actual protection layer or any like the layer that you're building the protection on is quicksand, and that's where all of the big money is within this. And then so that's why I think so many people are going to lose their shirts on this data aspect by not understanding this concept. I mean, mark my words, right? It's 2025. I think by like the 2 years, people will understand. And anyone that's betting like on these like data centers, what's it like 600 million or whatever it is on the data center, 6 billion, million, it doesn't matter. It's going to be pennies on the dollar within 2 years. And that's my promise on this. So if you like this type of content, please like, subscribe. Thank you very much.